Kia ora koutou, and welcome all to our May WMISA seminar. My name is Lorna Strachan and I'm a member of the WMISA committee and I'm organising this year's seminar series. WMISA is an international organisation and we wish to acknowledge Māori as tangata whenua and Te Taritio Waitangi partners in Aotearoa, New Zealand. We also acknowledge the traditional custodians of country and their connections to land, sea and community. We pay our respects to their elders, past, present and emerging. Indigenous peoples were the first Australian and New Zealand earth and environmental scientists, and we have a lot to learn from their deep knowledge that spans tens of thousands of years. The WMISA seminar series is about showcasing the amazing work of women in earth and environmental science in Australasia. All the recordings of past seminars are available on our website. You can sign up as a member of WMISA to get a notification of upcoming seminars, or you can follow us on Twitter. I'm delighted to introduce our May speaker, Dr. Juliet Sefton. Juliet is a postdoc in the Department of Earth and Ocean Sciences at Tufts University, Massachusetts, the US. She's a geoscientist interested in quaternary, coastal and sea level change. She specializes in fieldwork, sediment sampling and geochemical analysis. Currently based in Melbourne, she started her career as sea level researcher at Victoria University of Wellington in Aotearoa, New Zealand. So now it is my pleasure to hand you over to Juliet.
Thank you very much, Lorna, and it is a pleasure to be able to speak to you all. Can you see this in presenter mode? Yeah, okay, cool. Thank you. All right. So today I'm coming to you from the unceded lands of the Wurundjeri people here in Melbourne. I am a postdoc based at Tufts University, but I'm based in Melbourne right now, obviously, and I'll be starting at Monash University in July. So it is a great pleasure to get to know a little bit of the Geoscience Australia and New Zealand a little bit more. So today I'm just going to talk to you about the research that I do in terms of, how we research paleo sea level, and kind of use an example from my current postdoc project, which is on some small ocean islands in the Western Pacific Ocean in Micronesia. And as it seems to be tradition in these types of seminars here, I thought I would talk a little bit about how I got into geoscience. So I grew up in New Zealand, and I grew up in a little town called Wairau in the central North Island of New Zealand. And I grew up in the shadow of Ruapehu, and I used to spend quite a lot of summer times visiting some family in Auckland, where we have the Auckland Volcanic Field. And I remember quizzing my nana on the beach, looking out over to Rangitoto volcano and going, what's going on with that? And I don't think she had any of the answers for me, but it's one of my most earliest memories of being really curious about earth science. And ever since that, I would ask my dad to, whenever he went on a work trip, can you bring me back a rock? So I've kind of always just had this, this interest, inexplicably. And I spent most of my school age years in the South Island of New Zealand. I grew up in Christchurch, and I spent a lot of summer times either oceanside or in the Southern Alps. And, there's some really impressive landscapes here. And it was very easy for me to be really intrigued and curious about, what forms landscapes today. And so I studied a lot of different things. At high school, I did music, I did chemistry, I did geography. But ultimately, I decided to study geography and geology at university, mostly just because I was purely interested in it. And I had no other plan other than that. I was interested. And this kind of culminated into the 2010 Darfield earthquake, the first earthquake before the 2011 Christchurch earthquake. And I was there for that as a first year geoscience student, kind of experiencing this massive earthquake. And it just really hit home to me how much I loved looking into this and understanding this. And I really enjoyed my undergraduate degree. A lot of the field work, a lot of the lab work, and a lot of just the understanding of the processes. And towards like my final year, a lot of people were talking about what they were going to do next. And honestly, I had no idea. I didn't start doing this stuff with a plan of becoming a research scientist. I didn't really think that that was a career option for me at all. But at this time, it was also a bit of a downturn in the mining and the oil industry. So a lot of my classmates were like, well, I'm going to do a master's. And I kind of thought, oh, well, I really enjoyed university. I've enjoyed learning about this. So why don't I do that too? And so after that, I went on and did graduate school. I did a master's and I did a PhD, and I loved it. And basically that's brought me to where I am today. So I did a PhD after I did my master's at Victoria University of Wellington. I moved to the UK to do a PhD at Durham University and to study paleo sea level change. And that's where I am today. I would call myself a paleo sea level scientist, and because I use geological tools to reconstruct sea level over time. So as Lorna introduced, I sample a lot of sediments. I do quite a lot of field work, lab work. And yeah, at the moment, I'm just finishing my first postdoc and we'll be starting a new position at Monash. So hopefully want to do a lot more paleo sea level change research in this part of the world. So I'll move on to the research side of this presentation. So, and kind of start with, why is sea level not level? And not level in terms of how much it's not level, but also on sort of what timescales. So this is a schematic diagram of some of the processes that we think about as sea level scientists. And we're quite familiar with, sorry, my throat's doing funny things from talking a lot. We're familiar with a lot of the short-term processes that operate, days to weeks, months, possibly even decades. So we're thinking about, the tides, the waves, and what is the current weather doing? Or do you have a set climate phenomenon that's impacting sea level, for example, El Nino? And we can measure these with tide gauges. So, and we can also measure these with satellites. And we have some really good records for these over the last few decades and over the last few centuries. But these are not the only processes that cause sea level to change. There's a lot of longer term processes that operate over centuries and thousands of years. And these are processes like glaciers melting, tectonic uplift and subsidence, ice sheet melt and growth, and also a process we call isostasy or glacial-isostatic adjustment, which is where if our ice sheet melts and that water is transferred to the ocean, that's a change in the mass sitting on top of the Earth's crust, and the Earth's crust moves up or down in response to that. And these processes, because they are on centuries to thousands of years timescale, the way that we understand them and the way that we know about them is by measuring geological proxy data. And these processes are super important for understanding what might happen to us in the future, because these are the long-term processes that impact sea level. And just to highlight that a little bit more, I'm going to talk a little bit about the IPCC sea level projections. So the 2013 IPCC report projected sea level by 2100, given a business as usual scenario, to be about 1 meter of sea level rise. And the latest IPCC AR6 report, which came out last year, has roughly a similar estimate. So about 1 meter of sea level rise, like 2100, assuming business as usual. However, this business as usual is actually quite a conservative estimate because it's based upon the sea level and the ice sheet processes that we know really well, and doesn't really include some of those longer term processes that we don't know very well. And some examples of those are how ice sheets respond to climate warming. So this is what this dotted line is here, is a relatively low likelihood but quite serious sort of storyline that if some of the ice sheet processes that we don't understand very well do come to pass, we might see a lot higher sea level rises. But this also means, because we don't know, it means we also have quite a lot of uncertainty in our future projections. And if we push this out to 23,100, we could even get up to about 50 meters of sea level rise. It can't be ruled out statistically. So geological data is really key to understanding these long-term processes to improve the uncertainty of future projections. And what I was talking about there is the global sea level estimate. But how does that relate to real life? How does that relate to sea level in different places all across the world? Because all sea level is local. An example of this is this model here. This is from the rates of sea level change from the last glacial maximum 20,000 years ago until present. And during the last glacial maximum, if you have just an example here, if you look at North America, there was a really big ice sheet, the Laurentide ice sheet, that was sitting on the northern part of the continent. And as that melted and retreated, the land beneath it started to rise again as that mass was taken away, essentially. So at the moment, the net sea level change in northern North America is sea level 4. But immediately next to where the ice sheet used to be, the land was bulging up. And because that ice sheet is now gone, that bulge has started to subside, and we have relative sea level rise in blue. And all of that mass change has implications across the world, and sea level, therefore, can be really quite different from place to place. And this is just related to the glacial-isostatic adjustment process. But because sea level departs from the average, we need some local scale paleo data to understand these long-term processes in different parts of the world. So if we need a good geographic distribution of paleo sea level data to understand these longer term processes, we need a really good distribution of data. And this is a 2019 kind of compilation database of paleo sea level data around the world. And we can see that the North Atlantic is extremely well studied. And as a result, sea level projections there are probably much more accurate, and they have a really good handle on what type of sea level processes are operating at a local scale. And you can see that there's a lot of other areas in the world, so the equatorial areas, and particularly the Southern Hemisphere, like we always know, is really much more little studied, or there hasn't been a sort of big compilation to assess drivers at a bigger scale yet. So this is where I take you to what we're focusing on as our research project. And we're focusing on this area on the right here in the Western Pacific. So the way that we wanted to address that gap is by looking at these 3 islands, which are currently in a nation called the Federated States of Micronesia. So there's Chuuk, Pohnpei, and Kosrae. And these are 3 volcanic basalt islands that are now extinct. But as you can see here on the coastline, they have some really large old mangrove forests. And I guess if you were wondering if we just chose these locations because we just wanted to go on a really nice Pacific Island holiday, it's not the case, because there's so many mangroves. That's all there is. It's not a nice beach. But we went here to address this gap in relative sea level data And what we've found is some really interesting results that kind of contrast with everything else that we see in the region, and has some quite interesting geophysical implications and some archaeological implications. So I'll take you through that. So previously, a lot of studies had noted that there was at least 4 meters of mangrove sediments preserved in the coastal stratigraphy on these islands, and that they probably had a Holocene age, so younger than 10,000 years essentially. And for that to be preserved, there has to be some sort of accommodation space for an accreting sequence, or a depositional sequence to occur. So this is a really good target for a high resolution sea level reconstruction that we, in an area where we don't have much of this data. So our aims were to generate the sea level reconstruction in this area, Micronesia, using the mangrove sediment. And then from that, try and understand what are the processes contributing to relative sea level change in Micronesia. And we can do this, try to understand what are the processes contributing by thinking about relative sea level as this kind of sum of these processes that I've already talked about. We've got the eustatic component, which is the process of ice sheet melt or growth, adding volume or taking it away from the ocean, and also the expansion or contraction of the ocean as the ocean heats up or cools down. We also have the glacial-isostatic adjustment process, which moves the land up or down relative to the sea. We have some gravitational processes that I'm not going to go into at all, mostly because I don't really understand them. They're very complicated and mathsy and mass movement-y things, but it's still important that we know it. There's also some local tectonics is extremely important. So if the land is moving up or down relative to sea level, then that is going to really impact what relative sea level is at your location of interest. And there are also local processes that we have to think about. If you have a lot of sedimentation, for instance, that's going to change your water depth, and that's going to change where relative sea level is as well. So keeping that sort of equation in mind, I'll move on to, why would we want to use mangrove sediment specifically to understand past sea level change? So mangroves are quite a useful geological tool if we apply the present is the key to the past sort of mantra. And this is because mangroves around the world typically live in quite a narrow part of the intertidal zone. So in the schematic here, we have mangroves living between mean tide level and the highest tides. So the elevation range that the mangroves occupies becomes our uncertainty range on where we know mangroves live. So that means if we find a mangrove sediment in a core, we know that at that particular depth in the core, at that particular time, sea level must have been between mean tide level and the highest tides. And the other great thing about mangroves is that they're really, there's quite a lot of carbon produced in this system. So that means we have a lot of carbon available for getting a radiocarbon age. So we can understand the position of sea level in space, but also in time. So this obviously involves a lot of field work in mangroves themselves to understand this, present is the key to the past situation, and also to collect our paleo record, which is us collecting cores manually by hand, because realistically, that's the only way you can get your equipment into the field, because this is really quite dense, muddy stuff. So this is Simon and Byron, who are my colleagues, working hard, collecting the core. I'm clearly just standing around, just taking a picture of them. But essentially, it's a lot of work. And what we came up with for this particular project is a whole bunch of mangrove surveying. So measuring where mangroves live relative to modern day sea level. So this graph here is showing the position of mangroves within the tidal frame. So along the x-axis is relative water levels, mean tide level here, mean high tide here, and the probability that a mangrove occurs within this. So this kind of peaks around mean tide level and tapers off to the highest tides and the lowest tides, which means that we can use this, you can use mangrove sediment as a proxy for sea level in these locations. And I'll jump straight into the results. So this is our essentially our bread and butter graph for this project. Along the x-axis, we have calibrated age before present. So here is 8,000 to present times going from left to right. And on the y-axis, we have relative sea level in meters. So 0 here is present day sea level. And each of these rectangles is what we would call, as a sea level scientist, a sea level index point. And each of these represent the position of sea level in space and time. So the horizontal axis of these rectangles is the error that we get from the radiocarbon age measurement, and the vertical side of the rectangle is the uncertainty that we have from our measurement of where mangroves live. So the elevation range that modern day mangroves live in Micronesia. And we can also use all of this data, so the radiocarbon age error and the vertical error, and put this into a statistical model, which gives us the pattern of sea level change from about 5,000 years until present. And this is what this gray ribbon is with the black line in the middle. This is a 95% confidence interval. And what we can see from our proxy reconstruction is essentially a net sea level rise from around 5,000 years ago up until present, pretty constant. And this is probably a rate of about 0.7 millimeters a year. And this is really interesting because when you compare it to this dotted line up here, it's completely different. This dotted line is a glacial-isostatic model output. So it assumes a particular ice sheet history and a particular Earth viscosity, and it pretty robustly predicts a mid-Holocene high stand. And we see this mid-Holocene high stand throughout a lot of the equatorial Pacific, through other islands having corals that are preserved above present day or higher beach ridges. Obviously, our proxy reconstruction says something else in this location. And we also had a look in the field to see if we could find any raised corals or beach ridges, but we didn't find any. So we're kind of wondering, why do we have this serious sort of data model mismatch? So going back again to our sea level equation, what else contributes to relative sea level in one particular location at a particular time? So is it just because we plotted only one glacial-isostatic model? No, these are 4 different models that have 4 different ice sheet histories and Earth viscosities. And the mid-Holocene high stand in the equatorial Pacific and this region is a very robust feature. It does change magnitude-wise, it does change timing-wise, but it's pretty consistent. So it's not that. Is it, for instance, sediment compaction? So as sediment is deposited, it gets squished over time and the sample elevation tends to get pushed lower. So this is almost certainly happening on a small scale in these sorts of sequences, but that would, over 5,000 years, be on the order of about 10 centimeters. So sediment compaction isn't the only thing that's causing our data model mismatch. So is it some sort of subsidence? Is there some sort of tectonics going on? So if we look at where Pohnpei, Chuuk, Cosray are relative to active tectonic boundaries, so they're plotted here on this map in the pink, they're quite far away from these boundaries. And there's also no active volcanism happening at this time either. these islands are extinct volcanic islands. So it's not obviously this process. Is there some sort of oceanic lithosphere thermal subsidence going on? So as oceanic lithosphere is generated at a mid-ocean ridge, it's really buoyant, it's really hot, and as it moves away from the mid-ocean ridge, it subsides and cools down. So this is a process that is described at a lot of ocean islands, but it's unlikely to be a significant cause of subsidence here because this is some of the oldest oceanic crust in the world. So is it volcanic loading on the lithosphere that's causing some sort of subsidence? Is a weight like a volcanic island like these on the lithosphere causing localized subsidence? This process kind of happens over 10,000 years and would essentially begin and finish well before our record would have been deposited. So the youngest age of the volcanoes here, Kosrae, is about 1 million years old. So that process should have been and done. And another thing we could think about is there some sort of sediment loading from erosion, either locally or distally? A lot of the continents that would be a major sediment source to these islands are very far away and actually separated by ocean trenches. And local erosion and deposition should already be compensated. These aren't big islands. So we're still not quite sure what could be causing some sort of subsidence. So if you've got any ideas, it will be really interesting to talk to you. So we're looking, okay, we've got a data model mismatch. We can't really say why the subsidence is happening, but is there an independent evidence to suggest that our proxy record isn't just horribly wrong? There is a GPS station on Pohnpei. There isn't one on Kosrae or on Chuuk, but we're working with Makan Karigar at University of Bonn, and he calculated a subsidence rate of about 1 millimeter a year, plus or minus. And this is on the order of what we would need to explain our proxy reconstruction. So that's a work in progress. So we have our proxy reconstruction, and we think that there's some sort of subsidence that's going on that is a process we're not quite sure about yet. But we're pretty sure our proxy reconstruction is robust, and therefore this has some really interesting implications for archaeology in the region. So remote Oceania is what archaeologists call a lot of the oceanic islands that people migrated to around 3,500 BP. And this is significant because these are islands that you can't see from other islands, say in Papua New Guinea or in the Philippines. So they went out and colonized these islands. And a lot of their current archaeological understanding and a lot of these pathways are based off an assumption that the area experienced a mid-Holocene high stand and then relative sea level fall until present day, which is true for a lot of Pacific islands and the islands that I mentioned that had raised corals and raised beaches. But as we've found, it's not the case for our islands in Micronesia, which are situated somewhere around here. And as you can see, the arrows of current understanding kind of stop in this area. So where were people going? What were the pathways here? And if we dig into this a little bit more deeply, this is a map of radiocarbon ages from archaeological evidence across the region. So the red colors are older initial settlement ages, and the lighter colors are younger initial settlement ages. And the Caroline Islands is the colonial name for the the islands that Chuk, Pohnpei, and Khosrai are part of, so these three here. And these are, settled much later than counterparts to the west and the east and the south. And this is particularly interesting because the islands that we'd studied are high islands. They have a lot of land for agriculture. They have some more stable freshwater sources. And they're protected more so from storm surges or tsunamis compared to atolls like the Marshall Islands, where water sources are much more scarce and they're very vulnerable to extreme wave events, essentially. So, and the other part to this puzzle is that the people settling all of these islands had the knowledge and had the technology to make long distance voyaging and to discover new islands. So why would they miss these three islands and settle atolls instead? Or, why would they settle lots of other much bigger, grander volcanic islands and not some of these ones first? So our hypothesis is the quite anomalous sea level rise that we see at these islands from our proxy reconstruction has actually submerged a lot of the earlier archaeological evidence that would actually place the timing of arrival on par with its regional counterparts. So that's something that we're working on at the moment. And it also has some interesting, our proxy reconstruction has some interesting implications for the archaeology actually on the islands itself. So Pohnpei and Khosrai are the sites of Nan Madol and Leilu, which are UNESCO World Heritage Sites. And these really impressive monumental structures that are built from columnar basalt, kind of aligned really quite intricately, as you can see from this building here, and over really quite a large area. If you look at the remote sensing image on the right, so this is over over a kilometre of really impressive buildings, and this was built according to archaeology around 1400, and it was also interpreted initially as the Venice Pacific. And the reason for that is that these buildings are seemingly built today in the intertidal zone and are surrounded by these, what they call canals, or these shallow waterways that are filled with seawater. So if we actually use our reconstruction, sea level would have been nearly 1.5 meters lower at this time compared to today. So there's been 1.5 meters of sea level rise since it was built. And this means that these waterways at that time actually wouldn't have been flooded at all. It would have just been plain old dry land. So that makes us think, if you can see on the right here, we have this, what seemingly looks like a seawall. Is this evidence for some quite early adaptation to localized sea level rise? And is that a reason why this was not inhabited anymore? So, and it also kind of highlights that there's a lot of UNESCO World Heritage Sites that are probably at greater threat of rising sea levels than we've anticipated previously. So with that, I'll leave it there. Quickly summarize with a boring summary slide, I apologize. We reconstructed sea level change in Micronesia with mangrove sediments, and we find a difference between our proxy reconstruction and what glacial-isostatic model predicts. We think it's some sort of subsidence that's causing this data model contrast, and we're not really sure why. But what's really interesting is that this record of sea level rise may change how we think about humans settled Oceania, and may give us some insights on how people have adapted to sea level rise in the past. And a key take home for me from this research is that our subsidence estimate, our sea level rise estimate, is actually greater than what's incorporated into the recent IPCC projection for these particular islands. So it really demonstrates to me the importance and the utility of geological data and proxy sea level reconstructions to highlight, what's happening locally and how that might influence what might happen in the future. And I'll leave, this is my acknowledgements. There's a huge team working on this. This is an NSF funded project. And in particular, thank you to the COSRI and Pompeii forestry departments for helping us greatly in the field. So this here is Maxim, who led us through a lot of the COSRI mangroves and helped us collect a lot of samples. And he also caught us a lot of crabs for dinner, which was absolutely delightful. And I wanted to finish on a almost like a question for everyone, or a discussion point about how we should and can work with local Indigenous communities, as colleagues, and to avoid parachute science. And I'm more so reflecting on the science that we're doing with this project, as us as Western scientists have just gone into these islands, done some scientists, and then we're going to say this is how it is, and then go on about our merry way. And I want to do better, and I want to know how people work with local communities, Indigenous communities, and incorporate their values and knowledge into their work. So thank you.